And join on in chat message. Good morning to one and all. Welcome to the day 3 FDP of nanotechnology on healthcare. Due to some technical issues on live streaming, the program was delayed a little bit as per the schedule. Now, I would like to introduce our director, sir, to the gathering. Dr. Kumar V.S. Nemmani, Director, SVCP since April 2018. He holds his B.Pharm and M.Pharm in Pharmacology degree from Andhra University, Visakhapatnam. He has completed PhD degree from NIPER Mohali and subsequently postdoctoral fellowship from McGill University, Montreal, Canada. Dr. Kumar V.S. Nemmani has associated with 3 leading research centers in India. He was over 14 years of industrial research expertise and managerial experience. Over to Director, sir, and I welcome him to give the welcome note to the today's gathering.
Thank you, Ashok. Hello, everyone. Welcome to today's national webinar on nanotechnology in healthcare. I am overwhelmed with the type of responses that we are receiving from the day we started this webinar series. It is an overwhelming response in terms of the registrants, and the number of registrants had crossed more than 1,000. And the total number of colleges participating is also more than 175 colleges, and the states is more than 17. I think this number speaks the speakers, the panel is present for this webinar. I, on behalf of SVCP, the management, welcome all of you, and our chairman, sir, Sri Vishnu K.V. Raju Garu, vice chairman, Dr. Raichandran Rajagopalam Garu, our principal, Dr. K. Prasad Garu, and on behalf of all the staff, I invite you and welcome to this webinar series. I really thank you all for taking your time out and attending this webinar series in this webinar pandemic. And I must congratulate and thank Dr. Ashok being the organizing secretary, and Dr. Ramchandra Rao Garu being the program coordinator of this webinar series. So both of them put a tremendous amount of work in managing the whole program and inviting the eminent speakers like Dr. Harnath Garu. So thank you, sir, for accepting our invitation, being an eminent speaker. I know the NIT Warangal is the prestigious institute in India. When I was in college days, I have a dream of getting into engineering stream that did at NIT Warangal. So it is a very prestigious university, and you being the faculty in the Department of Physics and part of that NIT, I'm really honored, sir, for you accepting this webinar series. And I'm sure the participants in this webinar will be much benefited with your talk, and the amount of grants that you have and the quality and the publication that you are doing. I think I'm really impressed, and the team has appropriately chosen you. I'm really thankful, sir, and really welcome once again for this webinar series. So at this point of time, I'd like to thank all the principals and the senior staff who are continuously supporting every event that SVCP is organizing. And the same way goes for today's webinar too. So thank all the principals and the senior faculty who are supporting this. At this point of time, I also like to thank all the participants who are actively participating and in the question and answer session, and request them once again to give the feedback. With your feedback and your suggestions and your recommendations will continuously refine this process and make this webinar series highly successful. I'm sure this talks will be enlightening and enriching your experience, and you will be motivated towards the research, especially on nanotechnology. So with this, I once again thank and welcome you all for this webinar series. So thank you all. So over to Ashok.
Thank you, Director Sir. Now it is my privilege to present the brief profile of our today's guest speaker, Dr. D. Harnath Garu. He did his BSc from Nagarjuna University, Andhra Pradesh, MSc in Physics from Kakatiya University, Telangana State, and got the university first rank and gold medal. He did his PhD in Material Science from Shivaji University, Maharashtra, under the guidance of Dr. A.V. Rao. And regarding his experience, he rendered his services as a lecturer at Mahatma Gandhi Institute of Technology, Hyderabad for a duration of 2 years. He worked as a principal scientist at CSAR National Physical Laboratory, New Delhi for a duration of 80 years. And currently, he is working as an associate professor in the Department of Physics, National Institute of Technology, Warangal since 2018. To his credit, he is having two US patents, one Indian patent and one Chinese patent. Apart from that, many more are being filed and are in process. He had done many contributions in bringing out various book chapters, books, publications in various national and international journals with high impact factor. He guided around 6 PhDs and few more PhDs have been under guidance. He is handling around the 10 government funded projects. To his credit, there are many awards and honors received from various universities and national institutions and organizations. He is a life member of many professional bodies related to the nanotechnology and physics. And today he is going to present uh, as a part of our FDP3 is going to present a talk on nanotechnology and its application for cancer medicine. Now the session is handed to our guest speaker, Harnath Garu. Over to Harnath sir. Thank you.
Thank you very much, Professor Kumar Garu and Professor Ashok Garu, for
Thank you.
this opportunity to share some of my experiences and some of my research work towards cancer medicine. And I think this is a very apt platform, like nanotechnology and nanotechnology in healthcare. That's what the topic you have chosen, which is very apt to the present scenario. And everybody should associate with such type of research where some societal benefit is applicable. So today I am going to talk about nanotechnology and its applications, and particularly I am concentrating the application towards cancer medicine. So this is the topic of my talk today.
Sir, we can see your screen share.
Sir, we are seeing your screen share.
Yeah. Thank you. So currently I'm working as an associate professor in physics. You may be thinking that a physics person, why he is talking about cancer medicine. I'll come back to that one, why physics is important in that. And I'm associated with one company in USA, where I did my postdoc also and visited many times. It is Nanotheranostics Incorporation, which is there in New York, USA, where Dr. R.N. Bhargav, Professor Adosh Mehta, and Professor Alex Akimov, they are involved. And we are also involved in research related to the cancer medicine with a Albert Einstein College of Medicine, Joel Friedman and his co-workers. So they are the partners there. They do the animal testing and others. So this is what the brief introduction to this topic. So let me introduce my institute. My host institute is the National Institute of Technology, Warangal, which is one of the premier institutes and NITs in India. And this is our institute website, and this is our Department of Physics website, and this is my own research, where you can see the publications and other criteria of that. And the outline of my talk is divided into various subtopics. Like, let me introduce what is nano, how nano is different, what is the importance of these nanomaterials in 1 dimension, 2 dimension, 3 dimension, of course 0 dimensions also, properties and few applications of nanotechnology. But My concentration will be on nanomagnets. So they are used for contrast agents for MRI, contrast agents for MRA, and some recent results of oncology, which are image-guided intervention of cancer in conclusions and future trends, what we can expect in future. So this is a very broad overview. So some of the, maybe some slides are introductory slides. You may feel that they're too primitive. Please excuse me for that. So, so when a common man is introduced with the term nano, so what does he think? Basically, he remembers the nano car, but nothing is nano in this one. Nano is the smallest segment of cars. So that's why it is named as nano, but no nanotechnology is involved in that one. And here is another cartoon which I see recently in the newspaper. So a common man thinks that the small things will come out of this nanotechnology. This is not true. This is on a lighter mode, we can see. But essentially, nanotechnology refers to particles or technologies or devices that are very, very, very small in nature. And why do we go for small things? That let us see. So a nanometer, how do you define a nanometer and how big is a nanometer? So the first image you see that it is human hand, and this is a small portion, maybe 1 centimeter by 1 centimeter area. If you see, the whole scale is about 10 centimeters, the length. So if you zoom in, then you see, and then you start at 1 millimeter scale, you can start seeing the pores, sweat pores, and still you can see the sweat pore much bigger in size here when the scale is 100 microns. And this portion, when you enlarge it, then you start seeing WBC. So essentially, the white blood corpuscles, the cells, as having a diameter of about 10 microns. Still, if you take a part of that one and then zoom in, then you start seeing these strands of DNA. When the scale is about 100 nanometers. And still you zoom in, then you are able to see the atoms and molecules and atoms at the smaller scale. So a nanotechnology essentially deals with this range from figure number 7 to figure number 9. So that's the smallest thing which we are talking about. So these smallest entities, how they help us in achieving tremendous results that we are going to see today. So here is another description of size. This is an individual atom which is less than 1 nanometer, and is a human body. You see it is how big is this one? All pin head is about this much. So we are talking about very small range of sizes. So, so nanotechnology is essentially linked with biotechnology because biological entities and nanomaterials, they are in the same range. So you can have nanobiotechnology, and that can have much more implications to our healthcare and many other applications we can visualize in future. So nanometer, it is about 1 billion, that's 10 power minus ninth of a meter. For example, you see the hydrogen atom is about 0.04 nanometers. A protein is having 1 nanometer to 20 nanometers, depending upon the different proteins. The computer chip is 180 nanometers, and so on. These are various illustrations just to give the flavor that a nanometer is very, very small entity. Why people are fascinated for this word nano? Nano means dwarf in Greek. Dwarf means very small. So a nanometer, if you make a material in nanometric regime, then it can show properties similar to that of an individual atom or that of the bulk solid. So sometimes it is completely different, and what you see is what you don't expect it for normal conditions. So it's the nano thing is not new, as we were maybe we might have been hearing this since 2 decades. But you see, this is a cup called a Lycurgus cup, which is of 4th century BC, which is there in London Museum. You see that when you put light inside the cup, it is glowing red, and when the light is shined from outside, it is shining green. So it is having gold and silver nanoparticles which are embedded in the molten glass while making this one. So ancient Greeks, unknowingly they were mixing nano materials of metal nanoparticles, and they could see different light emissions coming out of that. So maybe because of funding and many other projects which we are receiving nowadays, we are thinking that nano is new, but it is a very age-old thing. Similarly, when you check up with the age-old church windows, then the color, it's not painted glass over the windows. It is the nanomaterials which are embedded into the glass. So maybe that nowadays churches, they may be painting such type of figures, but if you see age-old churches, ancient churches, so you see that the color is not fading. So that means they are embedded nanoparticles. And even you see nanotechnology in nature, like if you take abalone shells which you get it in the seashore, it you can see that along one direction it is very difficult to break, whereas in the horizontal direction or some other direction, it is easy to peel it off, easy to break. That is, when you see the same shell under ultra microscope, you see such type of layered structure. So along horizontal thing you can easily break it, whereas vertically it is very difficult. So each layer, each thin film of that thing, uh, thickness of that one, which is in nanometric. So this is another application, like in physics or chemistry. If you are talking about band gap of the material, a material, a bulk material will have a fixed band gap, a valence band and a conduction band, a fixed band gap. Whereas for nanomaterial, depending upon its size, the band gap changes. That's why we are getting different colors, like in like Argus. So nanomaterials, we can define it as the material which is having size less than 100 nanometers, at least in one dimension. Not necessarily all the three dimensions should be should be less than 100 nanometers. You can have a very big thin film sheet, thin film, where the one dimension, the thickness of that one maybe is less than 100 nanometers. You can call that as a nanostructured material. So you can have various classification, like one dimension nanowires is one dimension, it is being restricted, and the other dimensions it is not, like nano wire. The thickness of the wire is restricted, that is in nano, whereas the length and other properties, they are in the macroscopic scale. Similarly, if you have two-dimensional things, that's like thin films. The third dimension is again big. We can see that. Three-dimensional nanoparticles are like clusters, precipitates. The chemistry people know much better. And zero dimensions, they are usually referred as quantum dots. So zero means what? It's not exactly zero. It is almost negligible. If size is very, very negligible compared to an individual atom or similar to individual atom, then you can call it as it is zero dimension. So nanoscience is essentially the study and manipulation of materials in the atomic and molecular level. Okay, and that significant, which the properties of at this scale will be completely different from that of the bulk. Nanotechnology is the value addition to the nanoscience. Like, it will characterize and apply this nanoscience, knowledge of the nanoscience to some application. So nanotechnology is involved. See, these are the two sides of a coin, you can say. Both are important. Science is important as well as technological importance is also important. So we will talk about some science and some nanotechnology. So why we do feel that the nanotechnology is so special? It has many advantages. Like, it's an interdisciplinary field. As I told, that physics is required, chemistry is required, material science, biology. mechanical, electrical, medicine. So you should have a collective knowledge of all branches of science and engineering. Secondly, it is the science where individual molecules or atoms are related to the macro world. And thirdly, all the greatest challenges of human what we are facing, maybe COVID-19 or any other pandemic or inherent cancer, so many other ailments. So we have the challenge to counteract that one. So great challenges are ahead us. So for this one, nanotechnology or the engineering at the atomic level is very, very important. So you can see that engineering is the value addition, whereas these are the basic sciences. So if you have the amalgamation of everything, like you can have nanotechnology, biotechnology, material science and technology. So various aspects, various fields that can exist here. Of course, mathematics is essential for all branches of science and engineering, where you need to do many more calculations. So what does nanotechnology promises to us? It's not in not only medicine and health. So it influences information technology, energy production storage, material science, food sector, instruments, and so on. So in medicine, you can have target drug delivery systems, remedies which doesn't exist. So healthcare, everything that can be done, that are the promises that nanotechnology will give. Information technology, you see that the information is increasing day by day, and your laptop, laptop, and even the pen drives, the memory is increasing and the size is decreasing. So these are all the booms of nanotechnology. Similarly, energy production, storage, many other things. We will concentrate on medicine and health issues. So Albert Einstein has quoted in 1919 itself, like nature rarely surrenders one of the magnificent secrets. So why he quoted this one? What is the meaning of that one? He himself elaborated it as if you work in unison with the nature, means nature atomic dimensions, then we can overcome many barriers. And nanobiotechnology is $1 trillion industry. So this he has told in 1919 itself, which we are realizing now. So nanotechnology, you see that if you are engineering a nanomaterial in between 2 to 15, 2 to 10 nanometers or 2 to 15 nanometers size, quantum mechanics begin to dictate the properties. And even biological systems are in that range. So we can extend the non-linearity of the medicines, efficacy and other things. So you can have revolutionary things. Not only that, if you see the major industrial revolutions, like textile was a industrial revolution, railroads is a industrial revolution, the transport, automobile, computer, now nanotechnology. You can expect that nanotechnology can boost or it will impact all industrial sectors. By 2030, we could see many nano products that may be there in the market. So historically, if you see historical perspective of this, that in 1959, on December 26, famous physicist Professor Richard Feynman, he has delivered a lecture at um, he has delivered a lecture. The title of the lecture is "There is a plenty of room at the bottom." So, in a annual general meeting of American Physical Society, there he delivered this lecture. So what does it mean? There is a plenty of room at the bottom. It means that when you go to smallest and smallest entity, so there is a lot of scope for that. You can manipulate, you can play with the impurities or the dopants or the defect structures in the atomic scale, and which is very difficult. And if you can manipulate the things at the atomic scale or the nano scale, then you can do wonders. This was the pioneering lecture, and this is the link where you can have the whole lecture, which is given by Richard Feynman. So you can call that he was the visionary, where visionary for this nanotechnology, where but most of the people disagreed at that time, because They were not thinking that when you go to smaller and smaller entity, nothing can be done. So it was in 1959, but up to 1980s, people were doing few people were doing research on this reduction of sizes. But in 1980s, so the quantum dots and nanocrystals were discovered by Alex Akimov, Efros in Russia, and they have published a paper in Russian language. But fortunately or unfortunately, Bruce and co-workers in USA also they did the similar type of work, but with the chemical colloidal chemistry they did. Interestingly, both Ekimov and Bruce they worked with same cadmium selenide. So Ekimov, what he was doing in Russia, that he could take cadmium doped glass, and he has a selenium source with which he used to bombard that. So, so depending upon the concentration of cadmium, it's a less concentration, and used to bombard with selenium gun. So selenium, when it exactly collides with the cadmium present in the glass, so cadmium selenide was formed, and that was giving high luminescent light output, as well as there was a absorption shift. That was his discovery, but he published in Russia. But Bruce, he did the same cadmium selenide nanoparticles, nanocrystals, but using colloidal chemistry. He published in English language. So earlier, government of USA, they recognized Bruce as the father of quantum dots. But later on, Ekimov has claimed, because he said that he has already published that similar type of work in Russia. Then USA government has recognized now both these persons, Alex Ekimov and Bruce, both as fathers of nanotechnology. And interestingly, now because of the collapse of Russia, the Russians have moved to USA, and Alex Ekimov is associated with Nanotechnology Incorporation, where I did my postdoc. So I worked with Alex Ekimov. That's my I'm very fortunate to work with Alex Ekimov, who told all this story to me. So after this visionary lecture of Feynman in 1959, some people believed him and they started working on that. And with alkali metal nanoparticles, they vaporized and they could see some different properties associated with the metal. So later on in 1960s, ferrofluids, magnetic ferrofluids were discovered. So that also people have seen. You can see many videos that are there in YouTube. And in the early 70s, IBM has developed quantum well structures using xenon atoms on a substrate. And, the people started believing that nanotechnology is something new where one should think. But nature has been already having many of the entities in biological scale. For example, you take DNA. A DNA is thickness of DNA is in less than a nanometer. So if you blood cells and many are there were near to the nanometer scale. So proteins and other things. So biological entities are already there in the nanometer. So only we people have started working and making organic and inorganic nanoparticles in the nanometer. Here is an example where you can see 5 nanometer, very uniform distribution of iron oxide nanoparticles were developed by humans. So then they started, many companies came up and they started seeing, this is the periodic arrangement, you can see the particles. And cadmium selenide quantum dots, see, this is a pure cadmium selenide quantum dots, but having different sizes. The red one is having the bigger size, whereas blue one is having smaller size. So depending upon size, one can tune the colors. So that's what the people started working in that. And you can see after Feynman, many people wrote many books regarding that, like and Tanguchi has written, and Binning and Rover, and Curl and Small and Dexter. So engines of many other books have come up, and realization of this nanotechnology has come into picture. And another discovery I would like to mention, because I was associated this laboratory, Professor R.N. Bhargav of Nanotheranostics Incorporation, USA. So he discovered quantum confined atom model. So what does it mean? So if you are able to restrict the doping of a single atomic impurity in the cage of nanocrystal, let us say the nanocrystal is about 5 nanometers size, and you should have only one atom which is being kept in this one. It is very difficult to do that, and he could achieve it. So if you have that one, then this atom which is present inside the crystal will uh, will overrule the whole properties of the crystal. That's what he discovered. So many people did not believe on that one. How do you restrict and how do you claim that only one atom has entered into a nanoparticle of 5 nanometers? So this later on he has proved in zinc sulfide doped with manganese system, where atomic force microscopy and some other techniques he has used. See, these are the bright spots where you see highest luminescence, uh, light emission. So those they have analyzed and they could see that that has only one particle. If it is more than one particle, then you see the brightness has decreased. And if you pick this type of particles, and you can see that the sizes are very less, but a single atomic impurity can tune many properties of nanoparticles. So this is what he has developed. And later on, now what we are doing is we are putting a magnetic nanoparticle inside a caged crystal so that it can tune. You can call it as a pinning of magnetization. A single nanoparticle will make whole single atom. If you can introduce into a nanomaterial of 5 to 10 nanometers, the whole thing will become ferromagnetic. So that was the thing which we have patented it also. So that's the proof, you can say. And gadolinium oxide doped with europium, this magnetic nanoparticle, nanophosphorus also we have developed in 5 to 20 nanometers. Because the interesting part is europium is very good emitter. So red emission you can assign with europium, as well as gadolinium is good for having paramagnetic property. So you can have both luminescence and magnetic property associated, which are very useful for making for using as a contrast agent in MRI and MRI. So because already gadolinium chelate compounds have been used, people have been using those things for having a contrast agent. But the thing is, the chelates they are very sensitive. They can decompose in the body very with less time, and you can see the contrast going off. So inorganic particles, which we have developed at nanotheranostics, they are much more stable. I'll show some of the images. The main characteristics of nanoparticles, why do we go for this nanotechnology and nanoparticles, is that I told that the properties of this nanomaterial will be intermediate that of an atom and a bulk solid. So this is an example of gold material, and you see the surface to volume ratio is very, very important in this case. So a nanoparticle, why it is so important? Because it has more surface area. For example, you take a small cube of 1 meter. So the total surface area which is available for any chemical reaction to occur. So it has 6 surfaces. So 6 meters square is the surface area which is available for any chemical reaction or physical reaction to occur. Or if you want to coat with some drug, medicine, so it has only 6 surfaces, and 6 meters square is the only surface area which is available. But if I slice it into pieces like this, so in each small cube will have 6 surfaces. So the 6 surfaces are active. Earlier the inside the surface is inactive, whereas here it is active. So here the surface area increases to 12 meters. If I slice it to smaller and smaller segments, you see tremendously it is increasing. Okay. So another example I can quote it. Like you take a glass of water and keep it for drying at ambient conditions, temperature and pressure. See, the evaporation is only from the front side, and it may take a month to evaporate completely the glass of water. But the same glass of water, if I put it on the floor and just spread it, then within no time, maybe in a minute or so, the whole water will be evaporated. So what is important here is the surface. So if you spread, if you have larger and larger surface area, then your reactivity, your efficacy, many other properties, evaporation, and all these properties will increase. So more surface area if you have, then more volume of medicine can be accumulated in that. That's why when you go for a homeopathic medicine, they give small sugar pills, and they put liquid on that one. So the liquid will spread in the pores of that one, and slow release of the drug will be very essential for when you consume those medicines. So the surface area, you are increasing the surface area. By porosity also you can increase the surface because each and every pore has more surface to accommodate. So smaller the particle size, more will be surface area. Essentially, you should call it a specific surface area because surface area per unit volume is which is different. So nano, whenever somebody says nano means you are the first thing what you have to remember is you are increasing its specific surface area. So it's an example here. 30 nanometer particle have only 5% atoms on the surface, whereas a 3 nanometer iron particle has more than 50% atoms available on the surface. So another important thing which people generally use is quantum confinement. What do you mean by what you are confining basically? See, this is called when you in an atom when it is excited, you have electron hole pairs which are existing. See, the electron hole pairs are bounded pairs, they travel simultaneously. So these electron hole pairs, the distance between this one is called exciton Bohr radius. So this is fixed for any bulk material. So if your suppose the exciton Bohr radius is 5 nanometers and you have made the same material, whatever material has 5 nanometers, the same material you have made in 2 nanometers. So where does the electron hole pair will go? They will be squeezed, they will be restricted in the same particle. So that's what I wanted to show. So this is the exciton Bohr radius in a few nanometers, and you are making a particle lesser than that one. That means you have to squeeze. You cannot separate electron and hole. You have to squeeze that one and put it in this one. So this particle will be highly unstable in nature. So it is restricting, it is you are accommodating a bigger thing in a smaller capsule. So it will be highly energetic and highly what you can say highly reactive. So that's why when you make materials at the very nanometric region, you have to use it for you have to channel it for particular application. Like a small kid in your house, it is very difficult to control that guy. Is it not? He will be roaming here and there. But a bigger man you can control by saying some words. So a similar thing what you can assign is a smaller particle is difficult to handle. But if you channelize its energy, channelize its reactivity, you can use tremendous things for medical applications. So I'm just skipping some of the physics and chemistry part. There are weak confinement, medium confinement, strong confinement. The smaller the size, it's strong confinement, and bigger the size is a weak confinement, intermediate is medium confinement. So these are the density of states and other things. So as I told, this nanotechnology in nature is not new. Even you see some of the lotus leaves and other leaves, when you put water or banana leaf, so nothing will stick. It has all vertically grown nanotube-like structures. Similarly, photosynthesis process. See, the pigment is in pigment which is there useful for chlorophyll, useful for this photosynthesis. So that is in nanometric region. And spider web is in that one. And lizard, if you see that it can climb very smooth surfaces. without collapse, because it has many scale-like structures, and even this scaling like of structures, when you see under ultra microscope, you see that they are of nanorod type of structures. And in neurons, there are many crores of neurons present in our human body. So how they are interlinked, how the information is going to the brain, and how brain is reacting for that. So these are all the width of each veins and neurons. These are in nanometer region. Even when you see the structure of bone, human bone, it's not a single entity. It has small types of structures. So so nature is always, it is having many things already there in nanometer region. Even the kajal, the kajal which the girls use for their eyes. The importance of that one is it has some amorphous carbon and carbon nanotubes that are existing. So that carbon nanotubes, due to capillary action, it will drag all the dust and viruses which fell into the eyes when you go out. So that's why if, I named it as grandma's kajal, because if the grandma is there in your house, she will definitely insist to put kajal before you leave house. Not for increasing the beauty of the eyes, but the thing is it has some scientific reason. So the Lycurgus cup, anyway, I told about that. So the first paper which appeared is in 1908 in nanotechnology. Let me skip all these things. Here I'm just summarizing the things of which are naturally occurring things, and these are the man-made things which are in the nanometric region. So still it's not like a single electron transistor, many things, names people have developed, but still you see that the diseases which are hereditary diseases, you could not control. You see that some people in the hereditary, they will have diabetic patients are there, and at lesser age itself it will be transmitted to the younger ones. So can we take up this challenge and tune the DNA such that can we stop that progressing of that hereditary diseases? That's a challenge. Similarly, to eradicate all sorts of newer diseases which we are encountering. So can we put a full stop for that one? So these are all the challenges. Still, we have to work it out. So there are many properties that are existing for these nanomaterials. So, and there are many production techniques, like depending upon the size you require. So many physical, chemical methods that are available. I'm not going to any of these details of this one. So having a nano material is not just useful. You have to functionalize it. You need to impart a function to that one. Then only you can use it for any practical application, whether it is medical or non-medical applications. For example, to create a DNA biosensor, you need to have here. I just got it from the internet. Like gold nanoparticles were embedded into some um, matrix, and then that they could see that biosensing activity can be created in that one. The details you can get it from the reference. So here you see another interesting TEM image. I got it. So here satellite like of this one core material is there. Some ligands are attached, and then some other particles, small particles or drug molecules, you can say, you can attach it over here. See, here is the fabrication of silica gold nanoshells. So this is silica which is there at the center, and there are some small ligands attached to that, and these are the gold nanoshells. So this is also one of the uh, this is a cartoon, but these are the original pictures. The more number of gold atoms you attach it to the silica, it will become like this. 13, the scale is about 30 nanometers, so you can have this about 150 nanometers or so size of this. And these are the things which we can use it for some of the cancer medicines. Like uh, you can heat this particle, the shell of the particle, gold nanoparticles, by IR radiation. So locally you can cure some of the tumors by heating and annihilating at that position. So this is another example of the same nanoparticles which are put in the oils, and the blue one is the smaller one, and that is the bigger one. So here, see, you can, as I told, using nanotechnology, you can create wonders. Like, can you have a alloy of gold and silver at a time? Usually, gold is mixed with copper. That's what the goldsmith do. But you cannot mix gold and silver. But here we see the bigger particles. These are two types of particles. One is gold, and another is small one is silver. So you can have such type of entities which are not existing for the bulk materials. Similarly, this sensing and imaging applications, you can have this fluorescent tags which you can put it in the human body, and you can shine it with ultraviolet, and you can see the track of how it is progressing. These magnetic nanoparticles are very much useful for biomedical applications, because you can have a small magnetic nanoparticle, and this is green one is the therapeutic drug. So in order to release the drug, because you see for any cancer patient, drug is very important and it is very costly. So if we can coat this one, your particles with this therapeutic drug, and slow release of the drug will create the localized cancer cells. So by having this one, by using a small magnetic field, you can track it, or you can send that one to the tumor site, where it can go and then it can destroy the tumor. A small animation I'll just show you here. See, normally injection is given to the hand. Okay, so this is, let us say this is the tumor site. So when an injection is given, that if it is a heavy drug, then it will go from head to the toe, and most of the while traveling, most of the drug, it will create all side effects. That's why you see for a cancer patient, the paring of the skin, or you have the balding, the many other failure of heart, failure of lungs, or failure of kidneys. So all these are the side effects if you give more and more dosage. But if you there is a question that why can't we give directly here if you know that here is the tumor site? Okay, so if it is existing near to the lung or near to heart, you cannot give that. So the idea is for this drug delivery, you give the shot anywhere and concentrate the magnetic field here, so near the tumor site, the automatically the whole medicine will be accumulated at this point. So normally, if you give normal shot, only 5% of medicine will be going to the tumor site, whereas 95% will be roaming around, destroying all other organs. So by this mechanism, what we can do is you can give that one and concentrate the magnetic field here. Only you can give very less dosage, and everything will be accumulated here. Okay, once it is accumulated here, then how to release the drug? So you have the magnetic field, you just alter the magnetic field, means south pole to north pole to south pole. It's like taking a metal sheet and bending it on both sides. So if you do number of times, then you will see that metal piece will be broken into two pieces. Is it not? Similarly here, if you apply this one, so if you apply magnetic field, variable magnetic field, slowly the drug will be released. And importantly, what happens to the nano magnetic material? So you have to choose these nanomagnetic materials such that they are compatible with the blood or compatible with the human body, so that they just dissolve in the human digestive system, or they will just secrete through the kidneys. So it should not spoil, rather. So this is the direct injection and then delivery, target drug delivery system, which we are working with Albert Einstein College of Medicine, as well as with Nanotheranostics Incorporation. So, so these nanomagnets, I told the importance of this one, not only for contrast enhancement, but also to deliver the drug at the site. And this we have initiated way back in 2009 when we have seen a small article in Times of India, like nanoparticles as magnets can kill cancer cells. This initiated, and this is my work where manganese doped uranium sulfide. See, put a magnet and all the nanoparticles will be accumulated. Various color emitting nanoparticles have been made. This is a nanoparticle suspension. When you put a magnet, so everything will be accumulated within 5 minutes. The whole nanoparticles will be accumulated, and I made both magnetic and fluorescent nanoparticles. So when you shine ultraviolet, you know that all the particles are shining. So similarly, E. coli inhibition also we did with some zinc oxide nanomaterials, and which was appreciated by nature also. So many other things we started taking up. And here I am summarizing the nanotechnology. Let us concentrate on cancer treatment. The applications of nanotechnology is innumerable. Right from automotive industry, chemical engineering, bio, medical, construction, everywhere you have tremendous applications. But now we are concentrating on medical applications. So multifunctional nanomaterials, as I told, luminescent and magnetic, if you have, you can use for many other applications. Like even we could see that the fluorescence, which is very less for bulk, can be increased when you go to nano. So even we have studied many other systems where you could see that single atom emission also. The linear polar, a single atom is there, then you will get linearly polarized light coming out of European ion. So these are all various experimentations we did it, and we have tested all this in some of the some of the mices for the contrast and other applications. So merger of this nanotechnology and biomedicine, which is nanobiotechnology, which has tremendous future. So all these results still they are in the laboratory stage, because there are many protocols which we need to come up for the human trials. And this magnetic properties of nanoparticles, I told you that the same discovery which Professor Bhargav has done, that if it is a bigger nanoparticle and if you are putting a defect or a single atom in that one, it doesn't affect much. But if you squeeze that atom and then put it in a cage which is less than 10 nanometers, then the atom inside atom will experience uh, some what you can say quantum confinement inside the like a cage. So the same principle we have applied for magnetic also. So we have seen that a small nanoparticle, which is having all domains oriented in different directions. So if you put a, magnetic ion in that one, a single magnetic ion, then you can see all are lined up. This is called pinning of magnetization. This theory is not only for fluorescence, but in magnetic also it was very much influenced, and we have a US patent on this discovery as well. And I'm also a co-author of that one. So even we have studied many systems for that one, and even magnetic measurements also we could see in Sweden and many other places. These particles have only paramagnetism, or it shows ferromagnetic properties also? If it is really, if you are able to restrict one atom, it's very difficult. See, when you put as a chemical reaction, when you put the dopant ions, you cannot expect that all will get in, or a few atoms will get in. But if you restrict it, or if you pick the materials which has only single atom in that one, so then a few atoms also we can do wonders. So even the strategies which we are adopting is taking a magnetic nanoparticle, putting some ligands, and then put this one, or core shell type of structures, or amalgamation of drug molecules with the particles. So there are various structures which are available in the for this fluorescent and magnetic thing. People have been working on that. So our strategy is also similar to that. We take a non-magnetic material, put a magnetic ion inside, so it will pin, it will align all the nano particles in all the domains in one particular direction, and then put a protective coating on that. So let us see for the cancer medicine how it is working. Let us understand what is cancer. Cancer is nothing but a biological disorder. It's why you call it as a biological disorder, because you know that cell replication will continuously occur in the blood cells. But if the replication is done, and if some of the cells are not following the mechanisms or not regulated by the mechanisms, so you may call it as a dead cell, or you may call it as non-functional cells. So they accumulate and they create like a rebel type of system. So that is called the cancer. So we don't know who will get and who will not get, because if the number of cells which are existing in that one, if they are not following the regular biological phenomena, then that may create cancer. So what is the medicine for this one? There's nothing like no medicine for that. Only chemistry was very helpful in treating cancer, like chemotherapy. In chemotherapy, what they do, the cytotoxic chemicals they use to kill the cancer cells. They identify the cancer cells and they kill it. But the chemotherapy does the cytotoxic chemicals doesn't know which is cancer cell and which is normal cell. They don't discriminate between that. So the problem is that it will kill healthy cells also. So you will be losing both the things. If the cells are destroyed, then your immunity level goes down, and you will be catching some other ailments. So where does this physics comes into picture? See, in order to discriminate these cancerous and normal healthy cells, so we can see the mass transport mechanism and fluid mechanics. So these are the two fundamental things: the transport mechanism and fluid mechanics, together with fluorescence. So with this activity, we can easily identify which is a tumor cell, which is not, and how it is progressing, where to give the treatment, and all other things. So this is a simple cartoon to explain. See, if the blood vessels, these are the blood vessels, and these are the non-functioning cells which form over and above the blood stream. Okay, blood vessels. So what they do, they live by siphoning the oxygen which is present from the cells. By siphoning that one, they start growing. So what does the nanoparticle do when you give the nanoparticles to that one? So by siphoning, it will take out the oxygen, but due to osmotic pressure, you can have diffusion of these nanoparticles inside. So if you have the coating of that one, the coating of this medicine, that will kill these cells, as well as the, the cells which are there, which are present in the bloodstream also, they will be cured by this. So this is how the cancerous thing treatment will work. And the first step, what they did, instead of going for this nano particles, they have taken small molecules, small chemically, organically grown molecules they have identified. And this is the implanted tumor in the mouse. And first they implanted, and then they started giving small molecule treatment to that. Small molecules carrying the drug. So that they have simulated, and after 45 minutes, they could see the pixel by pixel slots of this tumor. And they could see that there are variations of the brightness all over this. But the problem is that this after 45 minutes or so, and the small molecules are very weak in nature. They penetrate into the cell, but they are quickly washed out by the bloodstream. So washing, like bleaching out the medicine. So instead of treating this one, you need to pump it more and more medicine, so that it should not carry out with the bloodstream. So then this was not a very interesting and important step. So then they went to the nanoparticles, the iron oxide nanoparticle, which I have shown earlier, 5 nanometer nanoparticles that they could see. And again, mouse implanted with this tumor at the site. See, how do you know that this is a tumor and this is not? Only the contrast will tell you. the thermal imaging, if you do, this is the thermal image. The thermal imaging, if you do, the portion which is affected will be much brighter in resolution. The much brighter in contrast. So if the temperature, localized temperature will be much more compared to that. So that will be bright. But when you give injection to this tumor with these nanoparticles coated with the drug, so slowly you can see that it will kill and it will come to normal and it appears dark in this way. So this is how you can see the progress of that. And today you can have these four famous criteria which is available. The Apraxane is one product which is from the Celgene Corporation, where they have albumin which is coated there, and this is about 150 nanometers. This is the chemotherapeutic drug they give it to the cancer medicine. Whereas Doxil is another product from Johnson and Johnson, where you can see that this doxorubicin is there at the core, and you have a polyethylene glycol coating, the protective coating, and some ligands that are there. So this is about 19 nanometers also. This product is also available in the market, but they are very, very costly in nature. And the Oroshell is another product by Nanospectra Biosciences, where I told you that silica core and gold shell. So where they give IR radiation, so due to IR, the gold shell will be heated up, and localizedly you can, by heating, you can localizedly kill the surrounding cancerous cells. And the other one is gold particle inside, and then TNF and PEG coatings on the outside. This is also to increase the heat, localized heat at that side. These are the four important strategies now which are available in the market, but all are quite expensive. So you can see that the progress of research or it has boosted from 1950 onwards. But if you see that how with time, you see the number of cancer patients are increasing day by day compared to some other heart diseases or cerebrovascular diseases or pneumonia, influenza, flu, and other things. So they are very less in it. This is increasing, and which is alarming, which we have to pay attention. Because if you by using nanotechnology or by any other thing, using early detection, you can have therapeutic drugs, and because they are very sensitive, and you can have dramatic results, improved outcomes for this one. So in vivo imaging also very useful when you use such type of nanotechnology based contrast agents. And therapeutics, localization and local heat treatment of that one, or on particle delivery of the drug. So these are things, all these things can be achieved using nanotechnology. There are huge market that I have briefed in the early stages. So it's a 100 billion market they are expecting. So, so intervention of this cancer using multifunctional magnetic nanoparticles. Why multifunctional? Because it is having fluorescence, phosphorescence, and then magnetic property, and then hyperthermia. You can increase the temperature, and many other things also you can use it, and you can use these type of particles for both target drug delivery systems or as a carrier to release the drug, control release of drug, to avoid side effects and other things. So diagnosis, tracking, treatment. So these are the three important stages. So you need to diagnose this rightly, and you have to track the medicine where it is going, and you have to observe the treatment. These are the main things which partly we have achieved for the first time using magnetic nanoparticles. So these are some MRI contrast agents. Just I will show you, because most of things are unpublished. So this is a magnifest is the very it's a gadolinium chelate compound, which is available in the market. So we are just comparing our properties of how the magnivest as a contrast agent works with that of our gadolinium oxide materials. So these are the comparative things. And magnivest for 3 to 4 hours it is quite stable. After that you can see that the contrast is disappearing, whereas for this one up to 10 hours you can have this one for magnetic nanophosphor materials. So for magnivest, what they do is for repeatedly for 3 to 4 hours they will give they will increase the dosage and they will give more and more chelates injected into the body. Whereas for this one up to 10 hours it is sufficient. You can see some of the MRI studies and oncology in mice using this, and all these experiments were done at Albert Einstein College of Medicine in Bronx. So you can see that how these magnetic nanoparticles allow spatial localization by having magnetic field. So this is the MRI contrast image. You can see here is the tumor cell because it is having more contrast. So when you inject it, and then when you inject the MNPs there and then put the magnetic field localized there, then you can see that it is collected over here, and with time you can see that the blackness is increasing, the brightness is decreasing. So that's why you are curing that. So the contrast, continuously you can see the contrast, and you can estimate how whether it is increasing or decreasing, or how much medicine is to be administered, and all these things. So you can, and even I told you the uptake as well as clearance of these magnetic nanoparticles through kidney. The kidney or the human body should not feel that these are the foreign bodies, foreign nanoparticles are existing. So it should be a biocompatible magnetic nanoparticle, which the body should accept, and slowly it should be cleared through the kidneys. That's the main aim of this study. So this is the comparison of this both magnifest and then our magnetic nanoparticles. You can see the dosage of this magnivest with that of this. The contrast, the more contrast, you will know much better the how to what is the dosage you need to give, the how much dosage is to be delivered to the right. These are all mice studies only. In 3 hours, you can see that gallium hydroxide doped with europium nanoparticles when they were pegylated, and albumin is injected to the mice. So after 3 hours, you see that the darkness. Earlier, the whole thing was bright. So by injecting that one, and slowly it is treating all the cancerous cells. So you can see within 3 hours means slowly you can improvise this biological moieties, and then you can see fast curing of this cancer in future. So these functionalization and the drugs for future you can have in various things, MNP, coating, antibody. This is the final product which we make it. Because of IP issues, I'm not sharing exactly how exactly we go further. So this is what our internalization, when our drug enters into the entity of the uh, cancerous affected cells, then slowly it will kill the cell, and it will kill towards the cell death. So these are the tumor growth of these nanoparticles. So there are different applications of this magnetic nanophosphor materials. So in vitro, in vivo, drug delivery. So these are the 3 segments where these things can be used. So these are the all boons of nanotechnology. Without nanotechnology, we cannot imagine all these things. So in vitro, we can do cell sorting, stem cell separation, enzyme immobilization, diagnostic kits and other things. And in vivo, you can have therapy, MRI, diagnosis, DNA transfection, angiography, and many other things, and target drug delivery, which we are concentrating now. So this is the X-ray based angiography and MRI based angiography, the importance of that one. And X-rays, they are harmful for the human body, the continuous exposure or prolonged exposure, whereas MRI based angiography is much safer, and much harmless exposure for that one. So, and cost is also almost 1/20th of the X-ray based thing. So in summary, I would like to say that incorporation of a single defect or a single dopant, a small cage of 5 to 20 nanometers of host, will enhance magnetic fluorescent MRI and many other properties. And bio-tagging or functionalization of these magnetic nanoparticles with biological entity or drugs will be very, very useful for cancerous tumor cells, killing of the cancerous tumors and other thing. And dosage also we can decrease less than 5%. What we use generally for chemotherapy, which we can minimize it. If you minimize that one, you are eliminating the major side effects, reducing pain and cost. And use of this magnetic nanoparticles, you can have faster relaxation rate because surface area is too high. And in maybe next few years, we can come up with medicines that are useful for this cancerous treatment. At diagnosis also, using nanotechnology, we can have more low cost and more precise and more fast diagnostic kits can be developed. And it's our dream to bring this one to India because testing even a small mice in USA is, have a lot of regulations and it is very costly also. So once a preliminary test is done, I would like to search for some entrepreneurs who can produce in India, of course, after doing pre-clinical and clinical trials, and we can introduce in India. That's the aim. It's a long-standing aim for all our team members. And these are the few things which we have already seen. Nano 2010, we have seen some therapeutic pharmaceutical drugs, nanoparticle thin film electronic devices, pigment paints. Nano 2020 on many biosensors, some functionalized fluids, some drug delivery systems. There some people are working on that. By Nano 2030, I think most of the nano biotechnology or the side-free effect less drugs and many more things which we can uh, see in future, maybe by nano 2030. So this is the flow chart or the expected flow chart, you can say. And those who wanted to work on nanobiotechnology or some other aspects of nanotechnology, these are the 9 grand challenges which US government has announced. And uh, not this has been adopted by most of the countries, including India, that if any of the person is working on of these 9 grand challenges, they will be funded. So whether you are working on nanostructured materials by design or manufacturing of nanoscale, chemical, biological, radiological, explosive detection and protection, nanoscale instrumentation and metrology, nanoelectronics, photonics, magnetics, healthcare, therapeutics, diagnostics, energy conversion, storage, microcraft, robotics, nanoscale process. So these are grand challenges which are identified for next decade. So if your research work is oriented in any of these one, so you'll be rightly funded by agencies. So finally, I would like to conclude with a small statement. Even a small, very small effect sometimes requires profound changes in our ideas. That's what Richard Feynman initiated. And these are the future readings. Those who want to read these readings, books. I'm just quoting here many references. So those who want to know about the history, evolution of materials, nanomaterials, nanostructural materials, cultural heritage, arts and cultural heritage protection by nanomaterials. So there are many other things. And finally, I would like to acknowledge all my students, research scholars at NIT Warangal for really working hard to do good research. And finally, I should congratulate the organizers of 1 week faculty development program on nanotechnology for healthcare 2020. I thank the chairman, sir, Sri K. V. Vishnuraju Garu, and my friend, and Sri Ramchandran Rajagopal, Vice Chancellor, Dr. Kumar, Director of SVCP, Dr. K. Prasad, Principal, Dr. S. Vidyadhara, Chairman, IPA, ET,
ఏలేదా ఆన్సర్
Dr. Ashok, and my friend Dr. K. Ramchandra Rao Garu, I think who has given my name to Dr. Ashok. And I thank all the teaching, non-teaching faculty of Sri Vishnu College of Pharmacy, Bhimavaram. And I'll be happy to answer. I am not a very great scientist in this medicine, but my role basically was to make the nanomaterial which are useful by the for the company, and there are various people are there. My portion is to make the nanomaterial, and nanotheranostics USA, they will pegylate it, encapsulate it, and Albert Einstein College of Medicine, they're the doctors, they do the clinical trials, and again they give feedback to nanotheranostics, and again feedback I'll get it, whether I have to tune the size, to the shape, all other aspects. So mine is basically
చూడండి సార్ క్వశ్చన్
materials related. So I'll be happy to answer a few questions if somebody. Thank you very much.
Thank you, sir, for your wonderful session. Now, I request the people who are in the Zoom can directly ask their questions, and the questions which have been posted in the YouTube chat box, I will bring to your kind notice, sir, for to answer them. Anyone in the in live in Zoom can post their questions directly to the guest speaker. Once again, I am repeating, anyone from the Zoom in live can pose the question directly to the guest speaker. Here are some questions from YouTube chat box. This is from Mohan Gandhi from Vasavi College of Pharmacy, Tadepalligudem, sir. He asked regarding magnetic nanoparticles, are there any marketed formulations available related to the magnetic nanoparticles for diagnosis or therapy?
See, the iron oxide nanoparticles, they are available in the market. That is Fe3O4. So that is there because earlier studies on this is done with magnetic nanoparticles, because you know that the human body needs iron. So they thought that iron oxide nanoparticles also will be biocompatible, and they have done some studies on that, and most of the studies have been done on that. But the thing is, there is a different aspect also, because because of this iron oxide, iron is being consumed into the body. So once you have that type of system, but the thing is, fluorescence is not available for this iron oxide particles. So tracking is very difficult in that case. You can tag it and you can use it, but you don't know exactly whether it is reaching the tumor site or not is a very difficult thing. And iron oxide has emission in the IR region, so infrared region. So that is the difficulty. So that's why people are moving to the fluorescent and magnetic nanoparticles. They are available in the market. The iron oxide is already available.
One more question. This is from Sheikh Arifa Begum, Assistant Professor from Chelapati College of Pharmacy, Guntur. Suggest any simple methods of preparation of these magnetic nanoparticles in the common laboratory without using any sort of advanced technologies. Are there any simple methods for the preparation of these magnetic nanoparticles?
There are many simple magnetic. You can make it in a small chemistry laboratory.
10 to the power of minus A.
I think most of the YouTubes, if you just Google it in the YouTube videos, also you can get. She can because I cannot tell the protocol here. If she can write to me, then I can send a simple preparation technique where they can make iron oxide nanoparticles in the laboratory, or even in the Google also you can find.
Sir, here one more question, sir. This is from Karthik Krishnamurthy, but he didn't mention his where is the designation and which institute he is from. His question is regarding the TDDS carriers, transdermal drug delivery system carriers. Uh, what are the challenges in targeting, especially in case of combination therapy?
Sorry, I am not that expert in medicine regarding
Okay.
that. Maybe they can post me the question, then I'll talk to my Professor Joel Friedman in Albert Einstein College of Medicine, and I'll get back some good answer for that.
Okay, sure. Thank you, sir. In this case, and instruction to all the viewers, whether through Zoom or on the YouTube, the email address of the SAR will be provided within the chat box. So you can pose your questions directly to the email, and within the short duration, he will be back to you. And with this, once again, I would like to conclude that today's session has been very wonderful, enlightening about the introduction and history of the nanoparticles. Apart from that, it was focused on the magnetic nanoparticles, especially the area of the work by the, our today's guest speaker, Dr. Harnath Garu, Associate Professor, National Institute of Technology, Warangal. And it is very an enlightened talk, and future perspectives and challenges are also being proposed by him. We are very thankful on behalf of the management staff of the Vishnu College of Pharmacy, and we are delighted to have you as a guest speaker for our today's session, sir. Now I declare the today's session, day 3 session of the FDP is being closed. Thank you, one and all.
Thank you, sir.
End.